Section 6.7 is about graphing and solving quadratic inequalities. A quadratic inequality is a quadratic function that has an inequality symbol. The way you graph them is the same way that you graph quadratic equations. And I'm going to list those steps right now. Step number 1 is you graph the boundary line. Here we're not really going to call it a boundary line. We're going to call it a related equation, because it's not a boundary line, it's more like a boundary parabola. And don't forget, when you graph the related equation, you have to determine if it's a dotted or a solid line. Step 2, you're going to test a point, and you find out if that point's in the true area or the false area, and then step 3, you determine shading. So here we'll graph this quadratic inequality by looking at the related equation with an equal to sign. We'll do that temporarily. A couple of ways we could do this. We could find axis of symmetry and vertex using the formula. We could also put it into vertex form. I'll do that because that's kind of what we've been doing. I took out a -1 here. Half of b is 3, squared is 9. So I'm going to add 9, which means I'm going to subtract 9 over here, but it's really not a 9 that I'm subtracting, it's a -9. So I'm going to subtract -9. So my new vertex form is x plus 3 squared plus 2, which means my h is -3 and my k is 2. So I know my vertex is right there, -3, 2. I know the parabola is going to open down because my a is a negative. Let's try a point like a -1 just to see what the y value would be. So this would be a 2 squared, which is 4, so -4 plus 2 is -2. So I found out that when I plugged in -1, I got -2. There also has to be a symmetrical point on the other side. So that should be enough to sketch it. It's going to be a dotted line because it's greater than, not greater than or equal to. It's a bad sketch, but good enough. So that's a sketch of my related equation. Now I have to figure out which side to shade. Do I shade inside of this related equation, or do I shade outside? Best way to do that is to find a point. I'm going to plug one right here, -3, 0. I like it because it has a 0 in it, and zeros are always great. So I'll plug that into the original. 0 is greater than -3 squared, -6 times -3, -7. So this is a 9 with a negative. This is a positive 18, and a -7. So 9 minus 7 is a 2. Is 0 greater than 2? That's false. Which means that -3, 0 here is in the false area. It's in the side that's not true. I want to shade everything that is true. So I'm going to shade all of this graph outside of my parabola. I'm going to try now to explain to you how we're going to solve inequalities using quadratic functions. Here, if you have a quadratic function that's smaller than 0 and you graph it and it opens up, because you want all the solutions that are smaller than 0, you're going to take the part of the graph that's below the line. Likewise, if your parabola opens down like this, you're going to take the part of the graph that is below the line, which would be this one and this part of the graph. And it'll make a little more sense when we do a specific example, but the point is, when you're less than 0, you want the solutions that are below the line. Likewise, when you have a quadratic equation that's bigger than 0, you want all the solutions that are going to be above the line. If it opens up, you want those two pieces, and if it opens down, you want this piece because it's above the line. It's greater than 0. Here, if you're using symbols like greater than or equal to, you need to include the x-intercepts in your solution. Let's see if it's a little clearer if we use a specific example. I want to solve this by graphing. So I'm going to begin with the related equation. I'm going to temporarily set it equal to 0. And because it's a trinomial, I'm going to solve this using the diamond. Two factors of -3 that add to be 2 are going to be -1 and 3. So we get x minus 1 and x plus 3 equals 0. Zero product property says my two solutions are x equals 1 and x equals -3. Now what does that mean? That means my parabola is going to cross the x-axis here at -3 and here at 1. Now I really don't care about a perfect graph right now. What I do care about is that the a, the leading coefficient, is positive, so I know that this parabola is going to open up into the air. And I really don't care exactly what it looks like. All I need to know is that it opens up like this and it goes through the points -3, 0 and 1, 0. Now to get to my solution, since I want my quadratic equation to be greater than 0, that means I want all the points that are going to be above the line. So I'm going to want everything that's to the left of this graph, because that's going to be up here. Now you don't have to shade this, I'm just doing it to show you. And I want all the spots that are going to be to the right of that. Now how do I write the solution out? I write it this way. I want all the x's that are to the left of -3. Or I want all the x's that are to the right of 1. And that is how you would write your solution. Notice I don't have greater than or equal to, less than or equal to, because it wasn't there. And notice that once I had my sketch, because I knew I had to be above the line, that told me which parts of the parabola I was going to write the solution for. Here's another example. I'm going to rewrite it using 3x squared minus 7x minus 1 is less than or equal to 0. I like to have it on the left so I know exactly if I'm bigger than or smaller than 0. This one's going to be difficult to factor. It's not going to factor. Completing the square is going to give me some really yuck fractions. So I'm going to use the quadratic formula here to solve that, the related equation. So I'm going to use opposite of b plus or minus b squared minus 4 times a times c. And that's all going to be over 2 times a. So this is really going to be a 7 plus or minus the square root of 61 all over 6. Now if I plug that into a calculator, I get some approximate solutions of negative 0.14 and I get 2.47. So those are my two x values that solve my related equation. Now I'm going to go over here to my graph. That's almost just barely to the left of 0, and then 2.4, 1, 2, about halfway between 2 and 3. So let's think of a sketch here. Because the a value is positive, I know my parabola is opening up. So here's my sketch. And now to determine the solution, I have to say I want all the values that are smaller than 0, which means I want all the stuff that's below the line, smaller than 0. So how do I write all those solutions? Well, I'm going to be between negative 0.14 and 2.47. And I write that by saying negative 0.14 is less than x, which is less than 2.47. So unlike the last example, this one's an in-between graph between them because I want all the values that are below the line because I'm less than or equal to 0. Now, looking at the less than or equal to reminds me that these should be included because they both are less than or equal to, so they are included in my solution. There's another way to solve these algebraically, and I'm going to start by setting it equal to 0 or actually making it greater than 0. So this is my quadratic inequality I want to use. I'm going to take the related equation and solve that. Now because I can do the diamond here, there are two factors of -6 that add to be a 1. There's a positive 3 and a negative 2. which means my two solutions are x equals -3 and x equals +2. Now instead of graphing this as a parabola, I want to look at it on the number line and see that here's 2 and here's -3. Now I know these two spots kind of represent my boundaries, so one thing that I can do using algebra is I can test a value in these three regions. We'll call this region 1, we'll call this region 2, and we'll call this region 3. So there's three regions. There's one that's smaller than -3, between -3 and 2, and then bigger than 2. So if I were to take a value that's in this area and plug it in, I want to see if it works. So let's try -4. I'm going to plug in -4. So that's going to be a 16 minus 4 minus 6. That's 16 minus 10 is 6. Is 6 greater than 0? That's true. So region 1 is good. Let's try something in region 2. I'm going to try 0 squared plus 0 minus 6. So that's going to give me a -6 greater than 0. That's false. So that's region 2 is the bad region. That's where the algebra does not work. And then region 3, I can pick any point that's bigger than 2 here. I'm going to try 4. So 4 squared plus 4 minus 6 is greater than 0. That's a 16 plus 4 is 20. And that's a 14 greater than 0, which is true. So what I found is that region 1 works and region 3 works. So I can write my solution based on that. I can say that x is less than -3 or x is greater than 2. But region 2 does not work. If you wanted to graph this, if you wanted to kind of compare this to graphing way back in algebra, you'd put an open circle on 2 and you'd shade to the right. And you'd say that all those graphs, or all those x values work over there. And then you put an open circle on -3 and shade to the left. And you would say all those x values work. And this is a way that you can solve this quadratic inequality by using algebra. Put them on a number line and then test the three regions to see if they work.